one, right? Like exact same as us.
Is part of it missing?
Yeah.
No, like it's
Exactly the same one.
Oh.
it's same mode.
No. I mean the graph. Is part of the graph missing?
Yeah.
Exactly. That's a good thing. Hang in there. Kiddos, what did you figure out for everybody just joining us? Guess what? These are notes. Write them down. We're writing two different things. We're looking at our calculator at two different examples. One is in the function mode. One is in the par mode. I've already put them in my calculator. Just real quick, once again, the line is this line right here. There's a function option, which is for the first example, and there's a par option that you'll see me model in a second. For the first one, I asked you guys to get a good window. Someone give me an example of your x min, x max, y min, y max that shows you approximately this picture. Look at your window if you have approximately this picture. Give me your x min. No. Mine's from some other graph. Give me your x min for this one. Function mode. Did no one get a good picture? Come on.
We're good.
Okay.
You sound so triggered.
Are we in function mode or parametric mode? Okay. Somebody in function mode who has this nice parabola. What's your x min? Negative 40. Thank you. What's your x max? Okay. I'm going to go a little bigger than 40 just because it looks a little like higher. So maybe like 60. Okay, what's your y min? Negative 40. How about your y max? Okay. So we like the 40s. Ready, set, maybe? Uh-oh.
Good job,
missing
JJ.
some.
Sorry.
No. I mean, you see it. Let me try 8.
There is no sorry. You just screwed everything up. Looks like Finland. Wait, is that the flag for Finland? Not the
Struggle. See?
Oh yeah, kind of does. I know you're talking about that.
100.
I think it's Denmark.
Could be Denmark. Got a lot of those Danes.
I think
Okay.
it's a Scandinavian.
Aren't the Danes great?
Voice is still not great. Shh. Okay. Whisper. So we have our function mode. We see our entire parabola, right? Cool beans. That was fun. Now let's go to parametric mode. If we use the same window, now I know this is zoomed in, whatever. I have this function plugged in. We use the X button to get the T. That's what happens in parametric. You guys notice there's an X and a Y, hence I gave you two equations. If you only put in one, it would not graph. Parametric comes in pairs. Hey, there you go. Good way of thinking about it. Question. Does your graph look like mine?
Not at all.
I know. Here's why. I bet most of yours probably, still graphing. It's from some other graph I did this year. Hold on. What do you guys have as your T min, T max right now without changing anything? 0 to
360.
360. Holy cow.
G max is 360.
Your 360, your poor little calculator is going to be thinking forever. What happens when you start at 0? Wait a minute. Where did that go? He's gone. And if you guys have 360, your little guy is like going, unless you're in degree mode. If you're in degree mode, beta cycli is real.
I'm in degree.
If you're in radian mode, it's just going to keep on thinking. And anyway, coming back. Parametric equations. In our calculator, the variable is always going to be t. Sometimes in equations, the variable can be theta. In your notes, you guys wrote down parametric equations are built upon a third variable, t. I want you guys just not to change that per se, but I want you to add to that for 1 second to see if my notes are actually ready. They're there. I want you guys to add t or theta, just to prepare you for some things that you might see in homework or in the future. Parametric equations could be built on t or built on theta. Long story short, there is a third variable. Where's my water? There is a third variable that x and y are built on. Without going into tons of like the physics as to what's going on, as to what you're working with, planar motion, two-dimensional motion instead of just one-dimensional motion, rectilinear motion. Long story short, we can talk about the actual path. Whisper. We can talk about the actual path that something is moving on with regards to x and y. There's an x motion, a horizontal motion, and a y motion, a vertical motion. And parametric doesn't just show us the where, it shows us the when. Now, can anyone figure out what that statement means and how it describes the difference between what we see here with t starting at 0 and going to some higher number versus what we see here on the top in function mode that has the entire parabola? Parametric shows the when, not just the where. T equals 0 only shows part of the graph. Why? What if I give you a hint? And what if I say the x-axis for a particular problem might represent the ground?
That's the starting point.
That like throwing stuff off of the cliff.
So maybe,
You can't come negative.
well, if the x-axis represents the ground, then if you throw something off the ground, where's it going to return to? The ground. So maybe this isn't even a perfect model for that. Maybe this is a better model for what Tyler said, which is you're throwing something off of a tower or off of a cliff, or you're shooting something up off of a tower or up off of a cliff. Why would that make a little more sense than the ground? What do you see here?
It goes through
It goes through the ground.
Because it goes through the initial point. So if you throw from a tower or project from a tower or from a cliff, you could throw it up, but it's going to pass the height of the cliff, and what's it going to keep on doing? Go down. So in physics, you can actually represent the x-axis or the height of 0 as different things. A cliff could be 0, and then where it lands could be negative as far as like how much below the cliff it lands. Or we could also say that this starting point is the ground, at which point if this was the ground, reasonably speaking, question, would there be any time greater than, hold on, look at your parametric graph. Question, when is it back on the ground again? So is it even reasonable for this model if you start on the ground and it comes back to the ground and it doesn't have a lot of force, and so it doesn't like form a crater in the ground, and so I guess it could go below ground level. Or you're not like throwing it in a pond, and so you could say like at sea level and it goes below. Anyway, there's a lot of exceptions I guess you could come up with. But let's just say normal, you're on the football field, which is not really practical for you to start from a height of 0, but that's okay. You're laying down, you need to throw something up and it lands. Where should our T max be in order to stop and have the correct model of motion? Time should stop at the x-axis, which just because we have a model and just because I've shown you some special points would be, in this case, 3 square root of 2 over 2. Oh, that's weird. That's an old way of writing a square root. Anyway, they must not have updated the programming language for this. So 3 square root of 2 over 2, if we were to graph that, would that give us a better model of what this little thing is doing? Yeah. And not only that, time doesn't just show us the where. Sorry, it doesn't just show us the when. It actually also shows us the which direction, which is something else that's new in parametric curves. Now, it doesn't show up in your graphing calculator because whoever did the TI programming did not model it to do so. But when we show parametric graphs, we need to show the arrows as well, because one parametric curve might have the ball or whatever you're projecting going this direction, whereas another parametric curve could be the exact same path going in a different direction. So, how we talk about that? I know. Is way down here in the word orientation. Oops, I'm changing the page on accident. There we go. Is the word down there orientation. Let me give you guys a couple seconds. Let's write a few more things about parametric curves. So it's another way of talking about functions It actually gives us more information, but it's going to be trickier for our brains because our brains have been taught, have been familiarized with rectangular functions, not parametric equations. So like we're used to seeing y equals x squared. We've seen it since algebra 1, so we're like, oh, no big deal, it's a parabola. Beginning of this year, we did like a function, I don't know, in an ideal world where there was tons of time for every class period, maybe like a block schedule or something. We would have made this whole like thesaurus, not thesaurus, that's not the right one. Collection, that's not the word I want, but that's okay. Collection of function graphs, everything from a line to a parabola to a cubic function to an absolute value function to a reciprocal function, that's 1 over x, to, I don't know if we go to quartix and quintix, but we could. Like all the different characteristics, how many branches they have, how many vertices they have, their increasing, decreasing nature, their domains and ranges, all that stuff we learned at the beginning of the year. We went over trig graphs, sine and cosine, exponential logarithmic graphs, all the extra trig graphs. We may not be perfect at them, but we have an idea of what they look like. Parametric equations, maybe you have an idea. Because those ones that you guys plugged in, there was a squared in there, so you might have thought it was a parabola. At the same time, they're going to be weird, and we're not going to be used to them. Because they define functions differently. They define functions differently. So we kind of have to go back to the beginning. In the sense of, okay, let's start with function notation. Y equals f of x. Yeah, that's great for function mode, for rectangular equations. For parametric equations, it's different. The x equation is going to be x of t. The y equation is going to be y of t. Perhaps it would be a little more accurate to do something in the forms of maybe like x colon instead. I could do something like x equals f of t, y equals g of t. But just to make things a little bit simpler, maybe I'll just go ahead and change this to be for the y equation, colon, for the x equation, colon. I'm going to have an x of t and I'm going to have a y of t. Or similarly in other examples, we could have like an x of, oh, no, it's way too thick. We could have an x of theta or a y of theta. Because remember, parametric isn't just t's necessarily. It could be thetas also. So first of all, parametric equations come in pairs. We've already kind of figured that out from our graphing calculator. What they graph, they're going to show a path. They're going to show what we call specifically a plane curve. It's like the path of motion, if you want to think of it like that. However, it might only be a portion of the path, because depending on the time interval, you might not see the whole thing. So think of the difference as function mode kind of gives you the entire road, or the entire road map of where something is going, the entire possibility. But the parametric equation gives you at a starting point where was something, and at an ending point where was it. It might not have covered the entire path. It might have only gone on part of it. And in things like when we were talking about ground level, well, there might not even be a path. I mean, if you were to draw like a dotted line on a picture, I guess you could show below the ground, but reasonably it's never going to go there. When you're throwing a ball or launching a rocket or other things that have projectile motion. So, if we're going back to the beginning, then we may as well go back to the beginning and say, okay, in order to graph these parametric, maybe we have to start at the very beginning, which when you first started figuring out how functions worked, you guys would make a table. Except, instead of making a table with, hey, plug in x, solve for y, now we're going to plug in d and solve for x and y. But how do we know what t's to plug in? I guess we could do the old school t's. We could say, oh, -2, -1, 0, 1, 2. Do you guys remember like those old school tables you would make when you were trying to learn quadratics or something? You would almost always plug in -2, -1, 0, 1, 2. But for time, does that necessarily usually make sense? Can you have negative time? Yeah, I guess if you think about it as initial time, like t equals 0 is 10 a.m., I guess you had 9:30. So I guess you could think about negative time as like what happened before. Not as in time travel necessarily, but oh, what was happening before when we first started measuring? Oh, it was back here. Okay, it could be negative time. But usually, where's time going to start?
0.
And you can plug in 0, 1, 2, 3. Speaking of how time only goes one direction, or does it? That's a much different question from not my class. Probably
That's a
switch.
physics question.
Depends on what you.
That's a
You should teach physics.
street theory.
We can talk about it in a different class.
We're not going to go into that type of physics if I did, but I'm not. We're just going to do time going one direction. Kind of like when we did functions. P.S. People on that side of the room, I'm not ignoring you. Remember, I'm just by the microphone because my voice is like, so hopefully you can hear me. If not, go watch the video. But time, we're going to have go only one direction, kind of like when we read functions for increasing, decreasing, we always went left to right. Time makes even more sense. You need to go from smaller time to bigger time because time only goes one way, at least for our purposes, for simplistic modeling. Anyway, I answered all that crazy time stuff. God is outside of time. I trusted him, so I'll leave it in his hands. Anyway, but you're going to plug into your equations and figure out what is an x and what is a y. And when you go to graph, you're going to graph the x, y points just like you always do. Time just tells you how many x's and y's you're going to have. And almost always they give you some sort of time interval. So we just need to watch out for some sort of time interval, like how they sometimes give us x intervals, y intervals. Sometimes they're just natural to the problem at hand, like if you're launching something from the ground, of course. Time is going to equal 0 and go until the object hits the ground again, then time will stop, etc. But if it's not some sort of practical real-life example, then they'll probably just give you a place to start time and a place to end time. Okay, increasing values of t, already talked about that. Find orientation. What that means is pay attention to, just writing in cursive because why not? You guys need to learn how to write in cursive to sign your name anyway. Pay attention to the direction of the movement. And then show with just a couple arrows. I'm just going to say arrows. You don't have to show a lot. Like you saw in the picture on the page before. Just a couple just to show the direction of the movement. And depending on the parametric equations, it might even be something that's like going around in a circle and just keeps on going and going and going. That's something else that's different about parametric equations. They're not bound by the function rule of the vertical line test, which is pretty nifty. Because not all motion meets the vertical line test. Things can definitely go in circular motion. All right, cool kids. So if I was to ask you guys to graph this equation up here, x equals t squared and y equals t over 2. Sorry, t squared minus 4 and y equals t over 2. T is in between -2 and 3. We're not given necessarily a real life example, but we just talked about how maybe time, I don't know what that was, maybe time can go negative if we're talking about like what happened in the past. We're just going to trust them and say, okay, we'll make our time interval between -2 to 3, just like you did in like algebra 1. You don't necessarily need to do -2 and -1.9 and -1.8. We're just looking for an idea. So we can use the easy numbers, -2, -1, 1, 2, 3. And how did they find for the beginning of the table? How did they find when t is -2, x is 0, y is -1? Yeah, just plugging it in. You would just find what is x of -2, plug and shove, -2 squared minus 4. which of course is 0. And then what is y of negative 2? Plug and chug, negative 2 over 2 is negative 1. So what point would you, from this resulting piece of information, what point would you put on the curve? No, negative 2 doesn't go on the curve. There you go. That's what you need to get used to. Negative 2 tells us, hey, it's included in the interval, so we graph that point, but we don't actually graph the negative 2. He's not seen in the graph besides the point, or besides the fact, I should probably say, that we graph the point because the time is included. So we would literally go ahead and, guys, just to save on time, I've given you the rest of the table. I didn't make you guys find it all. As long as you have the point of, or the idea that you plug in a time and get out points. Let's go ahead and take this table and let's graph it. And as you graph the points, you want to connect the points. Maybe not each time, maybe graph a few and see if you can get a feel for the motion, because we're not doing the decimals. It might be curved motion, like when you would make a parabola in the olden days, you would need to make it curved when you connect the points. And then see if you can figure out the orientation. Let me freeze the screen for just a second and I'll do it as you guys do. A place to put the orientation. Just show the direction of the movement. Do you guys agree basically with what I put? And do you see how very much your equations are not? It's not functional. They don't have to be bound by function rules. Totally fails the vertical line test, but something could totally work or move in this type of path. It could just be like a road around a mountain, right? Because you're going to go this way, then you're going to keep on going. You're doing like switchbacks. I guess that's for running. We call road switchbacks anyway. So graphing your points, once again, not bound by rules. As we're going, we're not going to be like a little kid that just kind of connects the dots and says, hey, a straight line, hey, a straight line, hey, a straight line, hey, a straight line. Like we can see that's curved, hopefully, or learn that that's curved, and then show the orientation a couple places along the way just to show which direction we're going. That makes sense, yeah? Not too bad? Okay. Now here's something tricky. You don't necessarily need to write down these examples. I want you guys to look and see. This looks an awful lot like what we just did. Except we just did this one where we had t is negative 2, negative 1, 0, 1, 2, 3. What's different about this one? The equations are different, but what else is different?
Direction.
No, the direction's the same. Check it. Good idea. Good idea, but no, the direction's the same. What values? The t values. The t values. So question, if these were modeling two different cars on the same what? Yeah. We could say the same road, just to be all particular. I'm just going to say the same path. We could say the same plane curve. The same path, right? Because it looks the same. They're on the same values as far as x's and y's. My question, if they're on the same path at the same time, are they going to collide? No. Are they going to take up two lanes? No. Why? They're there at different times. One is ahead of the other. Right? Which one is ahead? Can you tell? One on the right. Because it's there earlier. Does that make sense? So if we were to graph these at the exact same time, and maybe you guys realize why I'm using this little circle now to graph. Because if I was to graph each of these at the exact same time, he would have a circle and he would have a circle, but this one would be going faster. We'd be able to see that. As long as in your graphing calculator, you're using a little circle with a line so you can see the graph and where it is at a particular point. And one more thing you would need to change in your mode to see two things at the same time. You would need to change sequential, graph one graph and then the other, to simultaneous, graph them both at the same time. But if we graph them at the same time, the second one would be going faster. So same path, different, I guess we could say speeds, but for sake of simplicity, let's just say different times. Same path, different times. That's another pro to parametric modeling. That's not the right one. There we go. Now we're just going to basically start this idea. There's a few more things that we'll talk about with this on Monday, but kiddos, to be honest, we're almost done with these notes. So section 10.6 isn't super crazy. But remember how I was talking about we kind of have to reorient our thinking, not change it completely, just kind of get used to these new things called parametric equations that behave a little differently, aren't bound by the vertical line test. They have x's and y's for times, which means we might only see parts of paths because it's like how much they're actually traveling, etc. In order to compare what we aren't familiar with, what we don't know as much, to what we are more familiar with, to what we do know more about, the function versus the parametric in comparison to the function. It's going to be really helpful to learn how to eliminate the parameter, which basically means, in simplified terms, how to ignore the timing. How to ignore the timing. Because parametric, what's new? It has us think of not just the where, but the when. And not just the where, but the when and the direction. So we're kind of ignoring the timing and the direction, but in order to ignore the timing, I did not press my T, I apologize. In order to ignore the timing, we have to somehow get rid of the eliminate. T, the parameter. Eliminate, take it out. But as in all math, can you just randomly go into an equation and just take something out and be like, sweet, he's gone?
If you want.
I guess if you want, it's going to be wrong, right? Just randomly take something out and say, I don't like you. There's a life lesson in there somewhere. Process of finding the rectangular equation with the same path is another way of thinking about it. So we're going to try and figure out what the path looks like. Maybe not exactly where something is at different times. Just, okay, we just want to figure out the road, just want to figure out the path, just want to figure out the shape. Because parametric ones, again, do get confusing as far as what they look like. So, in simple equations, aka you have an x equation, a y equation, no big deal, we just have some t's. Simple versus a little bit more complicated where, well, still x and still y, but there's a whole lot more t's and they're a whole lot more entrenched in that problem. Ooh, even worse, there's not even t's, now there's trig and thetas. Anyway, going back to the simple. In the simple equations, the simple way for simple equations to find parameter is to follow these steps. Number 1 and number 2. Number 1 says isolate, which means what? Get it alone. So, find the x equation. There he is. And what are we supposed to do?
Isolate T.
Well, not yet. First step.
Isolate T.
Okay, get T alone. Well, guys, this is kind of old school algebra. Solve for T. In the olden days, when you were getting used to algebra, you would solve for different letters to move stuff around. So how would we solve for T? Yeah, if you have x equals 1/4 T, don't we multiply by the reciprocal of 4? Sorry, of 1/4? Or we can think of another simple way, but not everyone thinks that way, is just multiply the 4 to the other side. And then what can we say? Yeah, because some of you are like, I don't like it written like that. Okay, no big deal. You can write it the more proper way. But that's not the end. That's just the means to the end, in the sense that now that we have a t value, what can we go do? Plug it back in, and that's step number 2. So then we can just say, okay, y is equal to 4x quantity, careful, the parentheses squared, which means or implies y is equal to 16x squared. Now, not all of us would have figured out just by looking at this, like, oh, of course I know the path, it's 16x squared. But if we're able to eliminate the perimeter, we're like, oh, all right. So if we wanted to know the path, we can say, we know how to graph parabolas, kind of. And if worse comes to worse, we can just think of, we know the vertex at least. There's no h, there's no k, so what's my vertex? 0, 0, right? And then if we're like, we have no idea where to draw this besides to draw it up, we could do something like, okay, fine, when x equals 1, what's my y value? Super high, 16, right? When x is -1, what's my y value? Oh, super high. Okay. So now I have my path. Now question, kiddos, if we just stick to that rectangular, can we show the timing and the orientation? No. We can just show the path. If we want to know the timing and the orientation, what are we going to have to do? Go back to the parametric and figure it out. But it's a lot easier to graph y equals 16x squared than it is to graph x equals 1/4 t, y equals t squared. You know what I mean? So, you guys ready for a challenge? Last problem of the day.
I suppose.
I mean, do we have a choice?
Do we have like
Well, let's just see.
do we get our calculators for this?
Yes.
Nope. Figure out how to get t by itself in the x one, plug into the y one, place that and go. Moving up the ante. Anyone who gets them gets a package of gummy bears. Ready, set, go.
Oh, it's Haribo. That's disgusting.
It's like the classic.
I'm sorry, Tyler.
You
did you-
started making
Haribos
gummy
are like
bears.
eating rocks. Okay.
Oh.
Like I would just grab granite.
Well, then
from
you
the
don't get
road.
it. Ready, set, go. Although someone like I've taken up anyone else's.
Seriously.
I'm gonna freeze it and I'm gonna do it. Guys, party poopers. Oh, come on, fight T. Have some algebraic fun. You guys always complain wanting to go back to algebra. I just gave you an algebra problem.
What? You got a problem with it? What did you get? Like really did so good? That's fantastic. That's fantastic.
I think I did it.
What? The problem?
Yeah. I think I got the wrong answer.
What? It's awful.
Hold it up. Hold it up.
Who's this?
George Clooney.
Did he leave it in here or did you take it?
Yeah.
Okay, Steve, I'm not seeing how this disgusting equation is going to help.
I think I got it, but I don't know.
I have 1 over x squared minus 1 divided by 1 over x squared minus 1 plus 1.
I got x squared plus 2 over here.
Caleb, that's not right.
Close, Caleb.
Doesn't that mean that? Is it y because?
Yeah, I just didn't know how to get rid of the 1 on top
I
of
can
that.
simplify mine further, but I don't know how.
Okay, I got it. I put.
I don't know. It might be the same.
Anybody have it?
T equals.
I have it wrong, but.
Oh, you guys all gave up on me?
Yes, we're Americans. I'm not for trying.
Whoa. Okay. Wait, we gave it 3 minutes.
Yeah, we gave it 3 minutes and then gave up. What do you expect?
Yeah.
I think you had it right. You just didn't simplify, Tyler.
Yeah, I know.
Caleb, you were close.
I did.
Wait,
I
what did I
just
do wrong?
I didn't simplify it because
I don't know. I
looked at
didn't
it
hold everything in
and
the
stuck
head.
into it.
Okay, with
You have the 1 over x.
oh, you multiplied.
I multiplied up the square root and then divided the x. It was the easier way.
Oh, you multiplied. I think I know what you're trying to do. You multiplied by t squared. Okay.
Yeah. Because I don't like the division, so I.
Yeah, I was trying to get rid of the 1 by multiplying by 1 over 1. And I was like, oh, this is easy. 1, 1,
But it doesn't
1.
get rid of the division.
Yeah, it didn't look like it. Yeah.
So that
I was
was
like,
about-
this can't be. Okay.